All right, so this lecture will be about the PP wave correspondence and spin chains. I just realized there's nobody watching the chat, no? All right, so okay, so we've described in the last lecture the concept of a parallel plane wave. Oh, my God. We've described the concept of the parallel plane wave, or PP wave. So this was something where we had just one non-trivial function of x plus and the transverse coordinates, and we've said that there's only one component, only one non-trivial component of the Ricci scalar, and that is why we have that the linearized solution is actually exact. And we've considered these shock waves before, where we had the delta of x plus, and that corresponded to particles that were localized in x plus, so the energy momentum tensor, that was a delta function of x plus. But let us consider now the more general case where that is where there's no delta of x plus. And in particular, let's consider PP waves in supergravity. So in 11-dimensional supergravity, we have the solution written there. So the Laplacian of the harmonic function is proportional to a function f, that function phi squared, where phi is a 3-index antisymmetric tensor appearing in the 4-index antisymmetric field strength. But then an interesting subsection, an interesting subset of solution is the case where the harmonic function is quadratic. And further, then the most interesting one is the unique maximally supersymmetric PP wave, where it's a very particular quadratic function that's written there. So sum of from I1 to 3 mu squared xi squared over 9 and sum from 4 to 9, mu squared xi squared over 36. And so a generic solution, a generic PP wave solution, will have 1/2 supersymmetry, but there's a unique one that has the maximal supersymmetry. And the same thing happens in 10-dimensional supergravity. For instance, 10-dimensional type 2b supergravity. Again, PP waves have generically 1/2 supersymmetry, but there is a unique one with full supersymmetry. And in this case, it's actually, the harmonic function is just mu squared over 6 sum of I xi squared. Or, well, the constant in front is relative, so I define it as 64. Okay. So why are these PP wave solutions interesting? Well, it turns out that there is a certain theorem by Penrose giving the so-called Penrose limit, which says that if we go close to a null geodesic in any space-time, we see a PP wave metric. So the way to see that is we consider the null geodesic parameterized by u. So u equal to tau, and then v equal to 0, and also all the other transverse directions where u and v are like x plus x minus from before, they're light-like coordinates. And then yeah, can we get rid of that? Let's see. Oh, it's just this? Oh, okay. Okay. Oh, that's fine. Yeah, that's better. So we can always then put the metric into the form written over there. So we have this dv squared term with a coefficient alpha, and then du dv, which is like dx plus dx minus from before. And then beta I dxi dxi dv, or yi dv, and then some transverse metric. So this is part of the theorem that you can always put the metric in this form, where the null geodesic is defined by this. So it's parameterized by u equal to tau, and it's at v equal to 0 and y equal to 0. And then we take a rescaling of coordinates where u is fixed and v is rescaled by r squared, and yi are rescaled by r. Now, leads us to a PP wave, but not in the form written before, which was so-called Brinkmann form, but rather in a different form called Rosen. And, well, we can do some transformations of coordinates that are written on the page 158. But I want to point out the physical interpretation of this. So the interpretation is I can boost along some direction. So if I consider a point in the curved space-time, I boost along a direction, x. And then I take the limit where the boost goes to infinity, and also the scale goes to infinity. So I considered e to the beta goes to infinity, and r goes to infinity, where r is an overall scale of the metric. And then I identify the two, e to the beta with r. And the boost and scaling together lead to the PP wave metric. Okay, so what does that do for us? Well, we can consider AdS-CFT, in particular in the standard case of AdS5 cross S5 versus n equal 4 sub m mils, and consider this boost. Consider it along an equator of the 5 sphere and a point fixed in the center of the AdS cylinder. So AdS5 is the cylinder, and let me consider the point or the line at the center of AdS5. And then along S5, let me consider a boost or null geodesic that rotates around an equator of the S5. So specifically, then I write the AdS5 cross S5 metric in global coordinates as on page 159. So I have r squared, then minus cosh squared rho d tau squared plus d rho squared plus sinh squared rho d omega squared. And then for S5, I have cos squared theta d psi squared plus d theta squared plus sine squared theta d omega squared. So one considers this metric and then expand along. So this center is defined, this center line is defined by rho equal to 0. So that's the center of AdS. And this equator is defined by also theta equal to 0. So we expand around rho equal to 0, theta equal to 0. And we get the metric written there. Then define the null coordinates tau plus minus psi over root 2. So tau and psi were respectively the the time coordinate in AdS and the coordinate along the equator of S5. And then we do the Penrose rescaling. So the x minus, which plays the role of u, is, plays the role of V, is rescaled by R squared, and X plus plays the role of U, that is tau. It's not rescaled. Then we get this maximally supersymmetric PP wave in type 2B theory. So we've taken the Penrose limit. We've obtained a maximally supersymmetric solution. By the way, this is as it should be because we cannot lose supersymmetry by taking simply a limit on a solution, right? The solution has the same supersymmetry at all points in the limit during the taking of the limit. And since the original solution, AdS-5 crosses 5, was maximally supersymmetric, so is the final one, which is this maximally supersymmetric PP wave. But now, the interesting question is, what happens to the field theory? So what's the Penrose limit of the field theory, so to speak? And this is what we found in 2002. We found that this corresponds to, so let's say Penrose limit in n equal 4 square mils is a large R charge limit. So we can derive this, actually. So the energy in global AdS-5 is translations, corresponds to translations in global time. And the angular momentum J that corresponds to a rotation of x5 into x6. So one angular momentum among possible many is rotations in the psi coordinate on S5, because that is along the direction of the null geodesic. And then in the field theory, the energy corresponds to the conformal dimension. We have seen that when describing global AdS-CFT. And the angular momentum, so a charge for a rotation would correspond to an R charge for a U1 R charge that is part of the total SU4 R charge. And the SU4 R charge acts on SU4 or SO6, it's the same group. So we have, in the field theory, we have scalars xi that correspond to the coordinates on the brane, also denoted by xi, where I is 1 to 6. No, sorry. I should rather call them like here, 5 to 10. Just to make the same notation. So then there would be an x5 rotating into an x6 here as well. And that's the U1 that corresponds to the charge J. And then we see, by writing explicitly what P plus and P minus mean, that P plus, so the translation in X plus corresponds to delta minus J over 2. And P minus corresponds to, well, delta plus J over R squared. Okay, yeah, with a square root 2. So now let's think what that means. So we would like to consider, so P plus and P minus are momenta for strings in AdS-5, but moreover in this Penrose limit. So these should be string momenta on the PP wave. The PP wave being the Penrose limit of AdS-5 cross S5. So this should be held fixed. And then, so if P minus is held fixed, that means, and P plus and P minus are held fixed, there's only one possibility, that delta is approximately equal to J, and it scales like R squared, which actually goes to infinity, as we saw for our Penrose limit. Okay? So then, what does that correspond further in n equal 4 super M mils? So R squared in units of alpha prime, and as I said, alpha prime is an irrelevant dimensional constant. This is square root G squared Young-Mills n. So this so now if I, and this is square root 4 pi GS n. So if I consider the string coupling to be fixed for considering strings, then that means that from this relation it means that J goes like R squared, which goes like, excuse me, square root of n. So that means J over square root of n is fixed, right? And moreover, more precisely, I should say, I have that J goes like R squared, that for J squared goes like R4, which is G squared Young-Mills n. So more precisely speaking, we have that G squared Young-Mills n over J squared is fixed. Okay, so the limit that we are considering is a limit that is slightly different than before. So we considered large n, but now, and large n, and also large taut coupling G squared n, but now we also consider large charge J, such that the ratio G squared n over J squared is actually fixed. So how do we quantize the string on the PP wave and obtain something that similar from Young-Mills? So first, we write the general Polyakov action and specify the world sheet to be the world sheet on a PP wave, then obtain the formula there on top of page 161. One considered, as usual, the light cone gauge x plus equal to tau. So let's say strings in the PP wave. So light cone gauge x plus equal to tau. Then the length of the string, from this one obtains that the length of the string has to be related to P plus. And finally, when substituting this, and we have also, as before, the conformal gauge that square root gamma gamma alpha beta is delta alpha beta, or at alpha beta. When substituting that into the general action, we find a very simple action for the string, integral d tau, so 1 over 2 pi alpha prime, integral d tau, integral from 0 to the length, that is 2 pi alpha prime p, plus d sigma. And here we just have massive modes. So 1/2 massive scalar fields. So 1/2 minus x dot squared plus x prime squared plus the mass term, which is mu squared over 2 x squared. Okay, so it's a very simple action now, just a massive scalar field in 2 dimensions. And the equation of motion for that is the Klein-Gordon equation with solutions, plane waves, with omega being k squared plus mu squared, the mass term. And Kn is normally would have been n, but now we have rescaled in order to write down the length as 2 pi alpha prime p plus. We have rescaled by alpha prime p plus. Otherwise, the length would have been 2 pi. So we're considering closed strings. So because of that, the momentum modes on the circle of length 2 pi alpha prime p plus are n divided by 2 pi, n divided by alpha prime p plus. So the final formula for the excitations of the string is omega n is the mass square root, the mass term, plus n squared over alpha prime p plus squared. All right? So very simple. Very simple formula. Just, I mean, the only non-trivial thing is the mass term. Otherwise, we had a similar thing in flat space. And we can write down the Hamiltonian, which is just a free Hamiltonian for oscillators with frequency omega n. So it's a number operator. So A dagger A if you want, for the bosons, and B dagger B for the fermions. And then the frequency is omega n. So the only thing that remains is to rewrite this in terms of Super-Mills quantities. And we have seen that r squared over alpha prime was equal to square root g squared Yang-Mills n. And then p plus was related to delta minus j over square root 2. So, well, the square root 2 is irrelevant. One can make an overall rescaling. But, so the point is, the energy in this light cone quantization is basically P plus. So delta minus J. And 2 mu p plus, sorry, 2, yeah, 2, well, no, sorry, I wrote something wrong here. No, 2 mu p minus. Yeah, I think I made a change in notation, what's plus and what's minus. So 2 mu p minus now would be 2j, or rather I think, yeah, I think to be more in line with the standard notation, I should call this p minus and this p plus. So 2 mu p minus is now 2j over r squared, because delta is approximately equal to j, and so delta plus j is 2j. So so then what? So then by multiplication here with alpha prime, I get, so the 2 cancels, and alpha prime p plus is j times j divided by r squared over alpha prime, and r squared over alpha prime is square root g angle squared. So that means that in the end we have that delta minus j, which is omega n, or energy, right? Omega n over mu, dimensionless energy, becomes square root 1 plus, and then we have n squared divided by this thing, mu alpha prime p plus squared. So n squared g squared Young-Mills n over j squared. Okay? So this is what we should obtain from super Young-Mills. So how do we obtain that? Well, I said that we have a relation between operators and states in conformal field theory. So operators on the plane correspond to states on a cylinder. So if I want to construct the equivalent of these states, the states would live on a cylinder, but then the same thing would, equivalently, we could describe operators on the plane. So, okay, so let's construct operators on the plane that have this property, that delta minus j is square root 1 plus n squared g squared n over j squared. So the vacuum state would correspond to an operator so the vacuum state for strings, then this would be a vacuum state for the cylinder in field theory, and correspondingly an operator, and this would have 0 energy, and this would be an operator O0, let me call it, right? But 0 energy means it has to have delta minus j equal to 0, and we said j is large. Okay, and then oscillators. So oscillators for constructed with omega n. So the Hamiltonian was the sum over n and n omega n, just free Hamiltonian. And if I put let's say g Young-Mills to 0, so that this is 0, then delta minus j is 1. So at 0 coupling, in other words, when I don't consider quantum corrections, delta minus j, so the classical, the difference between the classical values for delta and j of the operator should be 1. So then oscillators, so it should be fields with delta minus j equal 1. Okay. All right. So what fields do we have? Well, there's a unique field with delta equal j equal 1 that I will call z, and it's the one that rotates, is a complex field that corresponds to rotations of x5 and x6, so x5 plus ix6. So this is a complex field, and rotations of x5 and x6 correspond to just multiplications by a phase of z. And then with delta minus j equal to 1, I can construct several objects. So things that I'll call phi m, which are the other x's. Let me call 1, 2, 4. So we had 6 x's. 2 of them are combined into z. And then the other x's are not charged under the rotation, so they have j equal to 0. But the dimension is still 1, like for any scalar in 4 dimensions. So I have these things, the 4 scalar fields. And I can also have the covariant derivative of z, right? So z, we said, has delta minus j equal to 0. But the normal derivative, as well as the gauge field, both have dimension 1, and they are not charged. So they have delta minus j equal to 1. So this indeed has also delta minus j equal to 1. So these are, and in here, these mu's, so mu equal also 1 to 4 are the 4 directions of the field theory. And here I have m equal to 1 to 4 for the 4 scalars. So I have 4 plus 4, 8 bosonic oscillators. And I can construct also fermions, some fermions, splitting the 8 fermions into 4 that have j equal 1/2 and 4 that have j equal -1/2. So the 4 that have j equal 1/2 will have so delta minus j of chi j 1/2. The fermion has dimension 3/2, and the charge is 1/2, so this is 1. So these are also 4 of them. Sorry, also 8 of them. Excuse me. Yeah, there are actually 16. So in total, there are 16 fermions. And I split them into 8 plus 8, 8 that have charge 1/2 and 8 have charge -1/2. Okay, and now I can match to what we've seen in the string theory. So in the string theory, well, we have 10-dimensional strings, but the two modes, the time mode and the longitudinal modes, are not physical, so we are left with 8 transverse or physical modes. So there are 8 bosons. And then it's a supersymmetric theory, so obviously you also have 8 fermions. So at least the numbers match, the numbers of oscillators. So now let's construct the operator. So the operator has to be constructed of z's, and more precisely out of jz's, because it needs to have the charge J, and the charge of Z is 1. So this operator is just, it's gauge invariance. It has to be trace Z to the J. All right? And then there's some normalization here. I don't care. And then among the oscillators, so these are oscillators of various levels n that correspond to that will correspond to some momentum in the case of the super mills. So let's consider zero momentum, n equal to 0. First zero momentum. So n equal to oscillators. Well, in that case, omega is still 1. So if omega is 1, I mean independent of GM mills, so if omega is 1, then I can only use these guys. And I have to use it in such a way that I don't get quantum corrections. Because, yeah, the formula for the formula that I obtained is independent of GN mills. So that can only mean that the operators must be these special operators, BPS operators, or chiral primaries. The ones that are in short multiplets, and therefore quantum corrections don't change their anomalous dimension. So these things are obtained by inserting these guys, phi m and d mu z, into the trace. So so I wrote here, for example, the one that has A0 dagger and B0 B dagger. So for the bosonic oscillator A0, I have the phi R, the index R, and then for the fermionic oscillator B0 with index B, I have psi B j equal 1/2. And then Z to the L and Z to the J minus L, because I can insert this at an arbitrary value and at an arbitrary position along the trace. And then, of course, I have to sum because all possibilities are equal. Or one, sorry. Now, you might say, well, why didn't I put this also at some arbitrary position? Because of the cyclicity of the trace. So because of the cyclicity of the trace, I can always put a single insertion back to the origin, and only the second insertion is relevant. So the distance between the first and the second insertion is a physical one. And then once I have this at excited levels at n greater than 1, I can just add to this a momentum wave function. Sorry, n L over J. Okay, with a n, so this will correspond now to n. All right. Yeah. So yeah, this afterwards people called BMN operators after our names, Bernstein, Maldacena, and myself. So what we will study are what we'll study is the so-called dilute gas approximation. It's a generic term. It just means that I have a very large number of sites, but a very small occupation number. So the sites are generically with a large distance between themselves. The occupied sites are generically with a large distance between themselves. And now we can show that for these operators that correspond to the string states, we can define a Hamiltonian that is equal to the Hamiltonian for the strings on PP wave that comes from this action. If I discretize it, so if I consider a discretized version of the string. So how do I do this? Well, I already told you a bit. I said that string states should correspond to states on the cylinder, and states on the cylinder are mapped in conformal field theory to operators on the plane. So on the cylinder, remember, I said on the cylinder, where this is time, I can define asymptotic states at minus infinity, and then a Hamiltonian action on them. A Hamiltonian action on them that amounts to translation in time. Okay. But this will be mapped, as I also explain a little bit, this will be mapped to a Hamiltonian action on the operators in the plane. So Hamiltonian acting on states n in R tau cross S3 via conformal invariance. This corresponds to a Hamiltonian action, which can only be a sort of commutator action on operators in R4. So to write the corresponding operators on the cylinder, I do a generalization of what I wrote before when talking about this operator state correspondence for conformal fields. So I write if this operator was a trace with many z's and few other things, I would call, the other things I would call impurities. So many z's, few impurities. Phi m and d mu z and chi j equal a half. So these things, when considering the state, this would correspond to just creation operator. And I would call the creation operator that corresponds to the Z, I called it there B dagger. And for these guys, I call it generically A dagger. So the state is something like what I wrote over there. With many B daggers, but a few A daggers in between. And there still needs to be a trace because all of these fields and the corresponding creation operators are still SUN matrices. Yes? Oh, well. So there's many B daggers to DL, some A, B dagger to J minus L, and so on. Okay? And this acting on a zero vacuum. And so how do I act a Hamiltonian, how do I define a Hamiltonian action on these states? Well, n equal 4 super m Mills has an interacting Hamiltonian which corresponds to commutator squared. And among these guys, I can take, well, I should have said x's. So among these states, I could take 2 of them, for instance, to be z's. Then these others to be phi m's. So this is one possibility. Yeah, and here it would be for reality of the interacting Hamiltonian, it has to be z bar. All right. And what does this correspond to? Well, so now if I write Feynman diagrams for the field theory, in particular for the 2-point function of the operator O, so let me call this O. So O of x, O at 0. I consider the 2-point function of this thing. So let's say here is 0, here is x. The tree diagram would be just something like this, where the double lines signify that this thing that propagates here is an adjoint. And so I would have these things. I would just have free propagators connecting the two. But then the first non-trivial diagram is when I have one interaction involved in here. So this comes with a G Young-Mills squared. And trace. So let me consider one interaction here. And moreover, let's consider this term. So this has, yeah, that's probably should have written the other way around with yellow. Better to write it like this. So now this would be phi m. And here it would be a z and z bar. Yeah, so the 2-point function would be O bar at x. And here would be z bar. Okay? So I have this Feynman diagram that contributes. This is the contribution at one loop. So at one loop, so one interaction, this would be the only Feynman diagram. Well, sorry, this would be one Feynman diagram. Then there would be another where the line is like this. And then there would be some that are of a different type. Let me see if I drew them here. Yeah. So you see in this page 165. So I have first the tree diagram. Sorry, the non-interacting diagram. Yeah, the tree diagram, let's say. And we're in the 't Hooft limit, so we only write planar diagrams. And then the two planar diagrams with this interaction are given here. But then I could also have things that, for instance, where there's a gluon in between two of these scalar lines, or there's a, let me make it like this so that it's clear, the a scalar bubble. So things like that, but when I consider all of them, So these diagrams correspond to basically completing the previous ones to something simple and without divergences. So once we identify what this Feynman diagram would do if it would be a Hamiltonian acting on such a state, the Hamiltonian is written on top there. So the Hamiltonian is, so there's a free part. So let's call it J. There's a free part like this. And then there's a part that has this coupling, G squared N over 2 pi squared. And in here I have phi j minus phi j plus 1 squared, where phi j is aj plus aj dagger over root 2. So you could see that this is basically killing a field phi here and creating it here. So if this is site j plus 1 and this is site j, so this interaction would correspond to, roughly speaking, a j plus 1, a dagger j. So that's one of the terms in here, and you can figure out that all of the terms are such that you get this Hamiltonian. But then you realize that this is the same as coming from a discretized version of this string on a PV wave. So here I wrote the action, but it's clear that the Hamiltonian is just changing the sign in front of x dot squared and removing the integral of a tau. So it's integral d sigma 1/2 x dot squared plus x prime squared plus mu squared over 2 x squared. Right? So this would be the Hamiltonian. And further, so I have x dot squared over 2 plus mu squared over 2 x squared. So this part is just a free oscillator, right? This is just the Hamiltonian of a free oscillator. So then if I have if I discretize the sigma coordinates, I turn it into a sum over j, and then this becomes j's. And so this is nothing but this free term, right? These are oscillators. And then I'm left with xj prime squared over 2. But the derivative when I discretize is just xj minus xj plus 1 squared over 2. So that's this term, okay? So it's really the same. Okay, so now now writing this string, this discretized string that corresponds to the operators, I noticed that there's yet another way of thinking about it, which is via a condensed matter analogy. I can think of this as a spin chain. So in any case, I considered a periodic, a closed string, so periodic boundary conditions. And then I have a number of sites, and I can say that in most sites I have, let's say, spin down, or, well, up I put there, doesn't matter. And only one site is different. And then I give this particle momentum along the circle. So that momentum amounts to basically that factor. Okay, that's the momentum along this circle. So this this excitation, it's what is known as a magnon for the spin chain, and this corresponds to our excitation for excitation for the string. And there's another way to define, a better way to define this. So when I wrote the operator, I considered the trace, and then all of these objects had SUN indices. But to take care of the SUN indices, I can consider something called Kunz oscillators, or even more precisely, because I need to consider only a few impurities among a sea of these other operators, I need to consider these so-called Kunz oscillators at the site. So those are things that don't satisfy the usual oscillator algebra, but a modified one. So for Kunz oscillator at the site, the algebra is as written there. So AI dagger is 1, but AI dagger AI is 1 minus the projector onto the vacuum at site I. So this, if I consider this, this takes care of the issue of the trace and of the necessity of planar interaction, planar diagrams only. And then we can consider the we can diagonalize the Hamiltonian by considering the following thing. So the first thing that we obtain, the first thing that we do is we think, as in here, that, well, we need to consider states with a certain momentum. So let's go to Fourier modes for the oscillators in the Hamiltonian. So let's consider Fourier modes like this. Aj is some 2 pi I j n over j a n 1 over root j. So now these are Fourier modes, which means with momentum. Further, we have a closed string, so in principle I can go in 2 ways into the closed string. I can go to the left or to the right. So the next transformation is to consider an as a sum of well, so yeah, to consider Cn, which is an plus aj minus n over root 2, and Cn tilde with a minus, right? That's the transformation over there. And finally, once I get to these C's and C daggers, the final diagonalization point is we can construct a Bogolubov transformation. That's also standard in condensed matter when you have some Hamiltonian that contains creation and annihilation operators. To diagonalize it in general, you have to look for a transformation that mixes creation and annihilation. And once you do that, you obtain just, in the end, just a free Hamiltonian. So H is sum over n. How did I call the last one? C. So Cn1 omega n plus Cn2 omega n. So omega n is actually the same. So the Hamiltonian is just a free, just a free Hamiltonian. And then, after all this, one finds indeed that omega n is square root 1 plus g squared Young-Mills n over pi squared sine squared pi n over j, which is even slightly more general than what we obtain for the string. We can consider a string that's slightly more general that obtains this solution, but it reduces to that if I consider n over j much smaller than 1, then I get the same result as this. Okay. So then finally, the diagonal states are these created by these things. So C dagger 1, C dagger n1, and C dagger n2. These are the diagonal states. And you look back at what they correspond to are they can be written in this way, and these correspond to basically the BMN operators, like written over there. Yeah, so one interesting thing is that this result seems to resum all interactions. You expand the square root, you get an infinite series in the coupling. Whereas somehow we've dealt with only the one loop interaction. But if you think about it better, it's not that the interaction was one loop, it's rather that you use the interaction Hamiltonian. So the interaction Hamiltonian is not necessarily, I mean, it's the Hamiltonian, and it's not really one loop. Okay, so how does that relate to the spin chain interpretation? So, yeah, this one loop thing, I don't think I don't want to discuss this. So the spin chain interpretation appears when you go beyond the this dilute gas approximation. So let me actually skip this part because I don't I'm not interested in it. So for the strings on the PP waves, we've focused on a U1 charge that we call J, and we considered only few impurities, so the dilute gas approximation. But now we can consider the most general case. So first, the full SO6R charge, and second, no impurities, just equal number of possible fields. And then the spin chain amounts to just considering operators, which are, let's say, trace of the whole, or maybe let me call it x's, xi1 up to xin. Right, so, or xij. So, yeah. Just a moment. This, I think this is too much detail as well. Yeah, it's too much detail. So let me skip the general story. So let me just say a few words. So for this general case, we can consider. So this is an object in SO6, and so I have the what I would call an SO6 spin. So it's not just spin up and spin down. It's something that has many values, right? But it's still formally, you can think of it as a spin. It's something defined at each site, and also in the most general case, these sites are all, you know, the number of excitations of different kinds are of similar numbers. So there's no impurity. There's no smaller number of some excitations. And then you can calculate sort of Hamiltonian for this thought of as a spin chain. I will not say the details because they're kind of a little bit complicated. The simpler case, sort of intermediate, is where I still consider the SU2 case. So SU2 spins. These are the usual spins, up and down. So the SU2 sector is defined by considering a Z as before, but now let me call it phi1 plus I phi2, and another, let's call it phi3 plus I phi4. And let's consider operators made out of only these two guys, but comparable numbers of Z's and W's. So O's, which are trace Z to some L and W to the J minus L plus contractions. Okay. Plus permutation, sorry. And then the interaction Hamiltonian, just like we saw there, it's a commutator squared. Just that now, if I just consider Z and W, this will look like this. So with GML squared. So trace Z commutator W, absolute value squared. And then one can calculate the Hamiltonian on the operators O. And what one finds that this Hamiltonian is G squared N, or 2 pi squared. Sorry, 4 pi squared. And then 2 times 1 minus the permutation of sites L and L plus 1. So yeah, I decided to not give too many details because, well, it's a somewhat non-trivial calculation. Yeah, and okay, let me say just in words that we can extend the concept of the Hamiltonian to something more precise, namely the dilatation operator. Remember that when talking about the operator state correspondence between the cylinder and the plane, we said that the Hamiltonian is mapped to a dilatation operator on the plane. So you can Hamiltonian in the Hamiltonian on the cylinder makes sense, but you can, if you think of on the plane, you should talk about dilatation operator, and yeah, there's a slightly more rigorous version of that. But then you turn this Hamiltonian into a dilatation operator. Never mind, it's basically the same thing. But the observation is that this this Hamiltonian is the standard Heisenberg Hamiltonian for the XXX 1/2 spin chain. Rather unfortunate name, but it just to contrast with XXZ and XYZ, which in this case so this refers to directions which are equivalent. So in XXX, all three directions are equivalent. Here, 2 of them are equivalent. Here, none. So so the Hamiltonian with rotational invariance, therefore in the 3 directions, is this. So normally you see it written as, so maybe you learned this in undergrad this way, that are the Pauli matrices or spin matrices in adjacent sites multiplied together. But if you rewrite this, you can rewrite this in this form with a permutation operator. Okay. So for the Heisenberg Hamiltonian, Bethe wrote what is known now as the coordinate Bethe ansatz, an ansatz to write the first single particle and then multi-particle states, multi-particle eigenstates of this Hamiltonian. So if I define so coordinate Bethe ansatz, I define the state x1, xn, the state as a state with n excitations with spins, with different spins, let's say spins down at positions x1, xn. And then the one, so, or m, I guess I used n for something else afterwards. And then the one excitation or one magnon, but with momentum, p, is just sum of e to the I px x. So like I drew before, you have this excitation, spin up or spin down, how you want to call it, that propagates along the circle with momentum p. Okay. So that's kind of obvious what to do. Well, it's a object that propagates with momentum p. And you can calculate its energy from the Hamiltonian. I mean, first you see that it's a eigenstate, then calculate its energy. And if you find that the energy is sine squared of p. So 8j sine squared of p1 over 2. But the non-trivial thing is when you have 2 particles or more. So first, the 2 particle state, or 2 magnon. So the 2 magnon state has to be something that depends on 2 momenta. And, well, so again, I write it as sum over x1, x2, psi x1, x2, x1, x2. That's just a parameterization going from state to wave function. But the wave function then is, well, so the first thing you might think, the first thing you should have certainly is the sum, I mean, the product of the 2 wave functions, right? So rather non-interacting incoming wave, let's call it. So e to the I px1 times e to the I p2 x2. But then the non-trivial part is a term where I interchange the momenta. So let's say you have a momenta that comes in with momentum p1, then with a momentum p2, and the 2 interchange momenta. But this process should happen with some S matrix, some amplitude for probability. This is called S of P2, P1. And you put this into the Schrödinger equation, you find that the energy is actually the sum of the energy of the 2 magnons. And moreover, you find a form for the 2-body S matrix. Which is psi of P1 minus phi of P1 minus phi of P2 plus I over the same thing minus I, where this phi of P is 1/2 cotangent of P over 2. So this was the first point of the Bethe-Ansatz, and then the second point is generalizing it to an arbitrary number of magnons. And not surprisingly, if the energy of 2 magnons is the sum, also the energy of m magnons is the sum. And by calling this phi of P, which was 1/2 cotangent P over 2, calling it U for rapidity, then you can write things in terms of U. So this is from the Schrödinger equation. So from the Schrödinger equation, you get the sum of the energies, the sum of the energies, and the form of the S matrix. But then you have to think of the periodicity conditions for this 2-body matrix, the 2-body wave function. And the periodicity conditions lead to the so-called Bethe equations, or Bethe-Ansatz equations. So periodicity of psi of P1, P2 resolves Bethe ansatz equations, which are written over there. So e to the I P1L is S P1 P2, and e to the I P2L is S to the P2 P1, S of P2 P1. So again, you can find the two Magnon wave function in this way, and you can see that this has the form of the BMN operator in the small number of impurity limit, and that's fine. That's what we were supposed to get. Yeah, so yeah, I'm not sure why I wrote this. Oh no, I remember. Yeah, so if I have a small number, if I still have a small number of magnons, that's much smaller than L, so it's still in the dilute gas approximation, and N much smaller than L as well. Then you find that by mapping to superior Mills, you find that this becomes approximately lambda over 8 pi squared, sum over k to 1 to m, pk squared. So it's a sum of momentum squareds. The ansatz for m magnons is a generalization of the ansatz for 2 magnons. So for 2 magnons, we wrote just an S of P2, P1. For m magnons, I still write the first term is still the product of all the terms of e to the IPX form. But then I can start interacting or exchanging in every possible way. So I can have one exchange or several. So I could write it something like this. I could write it in this form, but it's easier since the wave function is always, you can always multiply it by a phase. It will not change the probabilities. It's easier to multiply it by a phase and to write it in the form where, for instance, this 2 point would become, so if I write S as e to the I delta, if I multiply this by e to the minus I delta, this would be then e to the I P1 x1 plus P2 x2 minus delta 1, 2 over 2 plus e to the I P2 x1 plus P1 x2 plus delta 1, 2 over 2. Okay, so by multiplication with e to the I delta over 2, with e to the minus I delta over 2, I can write it in this form. And this form, you could see, is generalizable to the form I've written over there. But, okay. So the Bethe ansatz equations then still are obtained from periodicity. and they become a little bit more complicated. So their solutions are now called Bethe roots. The solutions of the Bethe ansatz equations are called Bethe roots. And one observation is that these Bethe roots, so the solutions are for, so these are sets of momenta, pi. The solutions need not be pi or ui or these objects, rapidities. So these solutions need not be real. What needs to be real is the energy. The energy needs to be a real number, real positive number. But the various momenta are not physically observed, so they could, the various rapidities are not physically observed, so they could be complex. And in particular, you can figure out that if there is a root ui, then there also is the complex conjugate. So for the Bethe ansatz, for the Heisenberg Hamiltonian, so I've described it to you in somewhat detail because there is a possibility to obtain something from the gravity side, but it's not so easy. It's not easily described. So, in particular, what one obtains from the gravity side is some continuous version of these Bethe roots, namely what goes under the name of thermodynamic Bethe ansatz, or thermodynamic limit. So it either means to be announced or thermodynamic Bethe ansatz. Yeah. I got a little confused. As far as I understood, in page 160, we use one loop computation to get to the Hamiltonian of page 166. Then the spectrum of this Hamiltonian leads to non-perturbative result on page 167. How can this be? Yes, so I said, but perhaps very very quickly. So so the important fact was, so there was one loop computation, but the one loop computation was just in terms of Feynman diagrams. So just in terms of the action on the Hamiltonian on operators. So so it's true that for that I used the one loop Feynman diagram in the planar limit, but the point was that so yeah, I'm not saying that this is a good explanation. I'm saying that this is what I believe is the likely explanation. That what one really defined in here was the action of the interacting Hamiltonian of Super-Yang-Mills on operators. So that is my viewpoint. Others might disagree, but because of that, by diagonalizing the Hamiltonian, we obtain this general form of, as you said, with a square root and g squared n and sine squared, which is a very non-trivial result. One which indeed appears as a sort of non-perturbative form. So my point of view is that it's really, what one really obtains is the action of the interacting Hamiltonian or super Yang-Mills, and that is what is being diagonalized. And it's not really the one-loop one-loop diagrams. So I know that other people might disagree, but the final result is there. You know, I did a calculation and obtained a final, very non-trivial result. So yeah, so I believe that's what's happening. All right. So the thermodynamic limit. So the thermodynamic limit is, so thermodynamic limit always means large number of particles of sites. So L has to go to infinity. And we also take the number of magnons to infinity. And then we try to derive equations for this limit. So in particular, we take the log of the Bethe-Ansatz equations and write things in terms of xi, which is the ratio of the Bethe root divided by length. And one obtains also that the relation between adjacent Bethe roots is like this. So ui plus 1 is ui plus minus I. So that means that, in particular, there's a real part, but then the imaginary part is I times the integer k. And so that means that these roots should be like this. So they're also, for every u, I have u complex conjugate. So I have two sort of lines. And then these relations are actually true only for small k, but when k becomes large, this starts to curve a little bit. So overall, what we find is two discretized lines that appear in the complex U plane. And these are called Bethe strings. And it is these lines, the Bethe strings, that are obtained from calculation in anti-de Sitter. Yeah, I actually hesitate to describe this calculation. I also have, I'm out of time. Let me see what I can say. So let me say just a few things in words. So one considers strings moving in an S3 subset of the 5 sphere, and then considers the motion, this classical motion, okay, using some particular type of algebra for this classical strings. One finds that the Bethe strings are in one-to-one correspondence with classical macroscopic strings. So I'll not describe this algebra because it's a bit complicated. But anyway, that's what I wanted to say in this lecture. So the final moral here is that we get the Heisenberg Hamiltonian at one loop, but the and the Heisenberg Hamiltonian has a beta ansatz solutions defined by the beta ansatz, and the solutions lead to beta roots, and in the beta roots in a thermodynamic limit, they lead to beta strings, which are in one-to-one correspondence with classical strings in AdS. Okay, so that was it. Questions? Yeah, question.
Sorry to go back to the first part, but what happens to the other background fields for the string in the BMN limit, and you take the Penrose limit and so on? Because
what happens to the other fields? What?
Yeah, like you have the B field, you have the Ramon.
Oh, you mean I see the limits of yeah. So I didn't say I didn't say for the specific case of AdS-5 cross S5, but I think I said it. I said that the solution involved the antisymmetric tensor field, which is which becomes instead of 5 tensor now becomes a 4 tensor field. So it's dx plus wedge a 4 tensor field, and specifically a constant 4 tensor field. And there's no B field for the D3 solution, and the D-Laton is constant. So that's it.
Okay. But then in the action that you wrote for that only has those like on gauge, those xi.
So the Ramon field couples the fermions. I didn't write the fermion part.
Okay, but it's there.
It's there.
It's those chi's that you wrote down.
Yeah.
So, okay. That's
so if I write the supersymmetric version, it will come from that.
Okay. Thank you.
Sure. Oh, okay. Just a moment.
Also, something from the beginning. What does R charge mean?
Yeah, I didn't define it very well. Yeah, so I said at some point that it's basically a charge that rotates the fermions. That's the most general way, I think, to describe it. It's a global symmetry rotating the fermions. So in the case of N=4 super Mills, it's an SU4 rotating the fermions, which also rotates the scalars. Okay, there's a question here. If there is a TT bar deformation of, is there a TT bar deformation of correspondence? What's the physical interpretation? Well, okay, so this is actually one of my latest papers, and I'm still not entirely sure what that means. Well, first of all, one would need to define what TT bar deformation means. So TT bar deformation is a deformation a deformation in 2 dimensions that preserves integrability and solvability and so on. So I tried to give an answer to that. I tried to give an answer to what would it mean to deform the gravity dual, what would it mean to deform the world sheet of the string, and finally what would it mean to deform the spin chain. And just to say a few words, for the spin chain, what seems to mean is that there's no, that you're just changing the definition of the U1 sector of the R charge, but you're going to an equivalent sector, and that's supposed to be kind of clear because you're still it's still an integrable deformation, and there's not much else that could have happened. So, but anyway, this is one of my latest papers, and if you want more, I'll talk about it at Integrability, which will be streamed online at IGST in Zurich. All right, let me just have a 15-minute break, then we can start with more questions and exercises. Oh, by the way, the exercises are already on the site, I think.